Have you ever wondered how a single discipline can completely decode the intricate biology of the human body and then, in the very same breath, predict the macroeconomic recovery of an entire nation? It sounds like magic, right? Well, today we're diving into an explainer that explores this fascinating intersection, the hidden engine that really shapes the world around us. We're going on a journey from abstract equations to concrete evidence. Because, you see, mathematical modeling isn't just a bunch of numbers scribbled on a chalkboard. It is literally the core engine driving scientific discovery. It's all about taking the messy, chaotic reality of our world and translating it into something we can understand, test, and ultimately use to make things better. Here is our roadmap for today. First, we'll look at the questions driving scientific discovery. Second, modeling complex phenomena with mathematics. Third, validating evidence through statistics. Fourth, building reproducible science with computation. And finally, empowering evidence-based decisions. Section 1. Questions driving scientific discovery. The starting point of inquiry. You know, every single scientific breakthrough stems from observing a real-world problem that just desperately needs solving. Every scientific discovery begins with a fundamental question. Whether we're analyzing the massive shock of the COVID-19 pandemic on international travel or trying to figure out exactly how to dose a life-saving medication, we absolutely have to formalize the problem first. Basically, you just can't solve what you haven't clearly defined. Section 2. Mathematics, modeling complex phenomena from problem to interpretation. So this is where we translate a real-world problem into the universal language of math. What we're talking about here is a rational pharmacokinetic model. Pharmacokinetics, that's just a fancy word for the study of how drugs move through the body. Now, instead of relying on those incredibly complex classical equations that are notoriously difficult to calculate, researchers came up with this elegant, mathematically tractable formula. By using applied calculus, this clean little equation lets us precisely track therapeutic windows. It proves exactly when a drug peaks in the bloodstream and just how fast it decays. Now, this might look like abstract math, but it actually has life or death stakes in a hospital room. Take a look at the parameters for a healthy subject. They show a normal drug elimination rate, setting our B value to 1. But for a patient with renal insufficiency, meaning impaired kidney function, that B parameter drops all the way down to 0.25. The calculus reveals that this fractional change causes a 100% increase in peak drug concentration, and it literally doubles the time it takes to reach that peak. The math directly maps to biological reality, ensuring doctors don't accidentally administer a toxic overdose. It's a total game changer. Section 3. Statistics, validating the evidence, the illusion of the perfect fit. Building a beautiful mathematical model is really only step 1. The truly rigorous part? Testing it. Let's shift gears entirely from biology to macroeconomics and consider international tourist arrivals in Nicaragua from the COVID shock of 2020 through 2024. A cubic polynomial model visually interpolates this data almost perfectly, curving to hit the actual data points right on the money. It even boasts an R-squared value of 0.971. That's a score so close to 1 that on the surface, it looks like an absolutely flawless predictive tool. But hold on a second. The crucial point is what happens when we stress test this perfect cubic model. We use a statistical method called leave one out cross-validation, or LOCV, which forces the model to predict data it hasn't actually seen yet. When we do this, the flawless cubic model predicts exactly minus 627. Yep, that is negative 627,000 tourists for the year 2020. A complete physical absurdity, right? There is literally no such thing as negative tourists, so our perfect model? Completely an illusion. When we bring in a multi-criteria evaluation system, that illusion completely shatters. While the complex cubic model dominates the in-sample fit, we have to look at the out-of-sample predictive error, which we measure here using the PRESS statistic. The simple linear model's error is roughly 431,000, but the cubic model's error explodes to over 2.6 million. Plus, the information criterion, which mathematically penalizes a model for being too complex, literally goes to infinity for the cubic model. At the end of the day, the humble linear model wins massively when it comes to true predictive validity. This really highlights a fundamental truth of statistical learning. The best-fitting model is not always the best predictive model. Especially when you're working with small sample sizes, relying solely on basic metrics like R-squared is severely biased. It tends to select overfitted models that just connect the dots to look good on paper, but they lack any real predictive power out in the real world. In statistics, every single additional mathematical parameter comes with a very steep cost. Section 4. Computation. Building reproducible science, transforming ideas into knowledge.
Let's be real. Human beings cannot run these massive cross-validation equations by hand. We absolutely need computational power to evaluate these theories at scale. This computational pipeline is the bridge between abstract theory and actual practice. It starts with raw data collection, moves into Python computational modeling, and then deploys those rigorous statistical loops. Finally, everything is shared under open science and FAIR principles. FAIR means the data and code are findable, accessible, interoperable, and reusable. This is the key to ensuring mathematical theories can be reliably tested and trusted by the global scientific community.
Using this exact pipeline, researchers were able to project Nicaragua's tourism up to 2030 using that winning linear model we just talked about. But they didn't just spit out a single magical number. Computation actually ran 10,000 simulations to create 95% bootstrap intervals, which provides a transparent range of predictive uncertainty. Look, forecasting 6 years into the future with only 5 years of historical data stretches that interval to 145%. Computation allows us to be incredibly precise, but it also forces us to be radically honest about the limits of our own knowledge.
Section 5. Empowering evidence-based decisions. Cross-disciplinary impact.
We've looked at these methodologies in isolation, but now let's consider their universal application. On one end of the spectrum, we're safely adjusting therapeutic windows to prevent toxic drug overdoses in patients with kidney failure. And on the exact opposite end, we are forecasting the macroeconomic recovery of a nation's tourism industry after an unprecedented global shock. Two entirely different disciplines, completely united by the exact same rigorous principles. It turns out the rules of evidence don't change just because the subject does.
This really brings us to the core philosophy of scientific discovery. Mathematics is so much more than equations. It gives us the foundational language to model reality. Then statistics steps in to rigorously validate that evidence, penalizing us when we overfit our data. And computational science acts as the engine, transforming those ideas into transparent, reproducible impact. Put them all together, and they form the absolute bedrock of interpretable decision-making.
I'll leave you with this final, provocative thought. As you look at the data in your own life, your own research, or your own industry, will your next decision rely on the visually appealing illusion of a perfect fit, or will you demand the rigorous truth of validated evidence? Thank you so much for joining us on this explainer, tracing the journey from equations to evidence.